Hello, I am Dr. Ethan, medical doctor radiologist, and in this video I will explain you the differences between the MRI and CT. I will also explain you very briefly and in simple words the basic principles of operation of these methods. MRI and CT are two of the most important and popular medical imaging examinations, but very often many people are confused and they don't know the differences of the methods as well as their indications. As medical equipment, they look similar at first sight, but they are absolutely different. The MRI stands for magnetic resonance imaging, and the CT stands for computed tomography. The MRI uses magnetic field and radio frequencies, and the CT uses X-rays, which is radiation. And this is the main difference. First of all, I will explain you the basic principles of operation of the two methods, and let's start with the MRI. The MRI function is based on the use of a very strong magnetic field. In practice, an MRI scanner is a big magnet. The usual strength of the magnetic field of a common MRI scanner is around 1 to 3 Tesla. This is an extremely strong magnetic field, and just for comparison, the magnetic field of an MRI of 3 Tesla is around 60,000 times stronger than the magnetic field of the Earth. Apart from the strong magnetic field, MRI uses radio frequency to operate. We are taking into account that the human body contains water of around 70%, and the water molecules consist of 2 atoms of hydrogen and 1 atom of oxygen. The atoms of hydrogen are the useful part of the water in our case. Human body is full of hydrogen atoms, which are protons with positive electrical potential, which in practice they are spinning protons. So they produce magnetism. So you can imagine that the human body is full of billions of microscopic spinning magnets. The idea is the following. Let's have a look at this part of the image. At any moment in time, all the billions of hydrogen protons in our body are all orientated in random position and spinning on their axes. The spinning motion is known as precession, but if we apply a strong magnetic field, let's have a look here. If we apply a strong magnetic field on the human body, like in the case of an MRI scanner, the axis of the orientation of all these billions of hydrogen atoms, the small magnets in our body, will align along the direction of the applied magnetic field. In other words, the axis of the protons will be parallel to the magnetic field direction. Of course, some of them will take opposite orientation, and some of them will face either to the north or to the south pole of the magnetic field. According to the quantum physics, there are always just slightly more up protons than down protons. Another interesting point here is that the total magnetic field generated from all our body hydrogen protons, these tiny magnets, almost cancel each other out to leave only the magnetic field from the small proportion of these extra up protons, and it is this small magnetic field that we can measure using MRI. The stronger the magnetic field, the faster the protons they spin. So how do we distinguish the tiny magnetic field caused by the extra up hydrogen protons in our body from the massive magnetic field of the MRI scanner? How we detect this magnetic field? In this case, we use something we call radio frequency, or RF, and the next step is to use a coil, which is a radio frequency transceiver, and we use a special radio frequency or RF pulse to disturb or flip all the protons at the same time out of alignment from the scanner's magnetic field. There are different types of coils designed for different parts of the body which are planned for examination. The coils act as radio frequency transmitters or receivers, like antennas. The MRI function schematic in this picture, it is probably a little complicated, but just keep in mind that the frequency of the RF pulse must be the same as the frequency of the spinning hydrogen proton, so they can exchange energy, so that they are on a resonance with each other, hence the term resonance in MRI. Now, how we get the images? I came back in the previous image I showed you, and what we see here that at the time we turn off the coil radio frequency transmission, the protons flip back and realign along the main magnetic field on the MRI scanner. When the protons flip back and realign with the main magnetic field, they give off some energy. It is like the released spring, which releases the dynamic energy it keeps as long as it is compressed. Just keep in mind that different tissues in the body give off or give back different amount of energy. To measure this emitted energy, we use the coil which is placed around the body part we examine, for example the brain, and the coil acts as an antenna in this phase and detects the released energy which is conversed to an electrical current, and because the energy which is sent back from the protons is different from tissue to tissue in the body, it is transformed by a computer using a mathematical calculation called a Fourier transformation into the image. Because protons in the different tissues of the body all give back different amounts of energy, the result of the transformed energy is a result of a highly detailed image of the tissues inside the body. So, in conclusion, the MRI uses strong magnetic field and radio frequency from a coil. Remember that the coil acts as a transmitter of the radio frequency as well as a receiver of the radio frequency. So, in other words, what we measure finally is the signals of radio frequency returning back from the flipped spinning hydrogen protons of the body, which turned to small electrical signals of different energy, and after a computer mathematical analysis, finally the image of the examined part of the body is produced. Of course, I would like to notice here that the whole procedure is much more complicated and complex, but further explanation is out of the scope of this video. Here are some images from an MRI scanner, and now let's explain the CT. What is CT? CT uses X-rays, and X-rays are produced the same way as they produced for the simple X-ray pictures, but instead of a simple film, In CT scan, we use a series of detectors. Here we see the X-ray source, and here are the detectors. The detectors are always placed opposite to the X-ray tube source. The body, the human body, is placed in between on a moving table, and during the X-rays production from the X-ray source, the table and the human body move to one direction, and the system X-ray tube and detectors are rotate around such a way so a spiral scan is made. And what happened? The patient is in between the X-ray source and the detectors. And the X-rays penetrate the body, and the detectors detect the photons which are produced from the X-ray source and exiting the body. The principle is the following. Let's see this image. This is the X-ray source, and these are the detectors. Here in between is the human body. All the photons, before they strike and penetrate the human body, have at this point the same intensity, the same strength. But because the human body is consisted from tissues with different density, the photons during the way through the human body absorbed from the tissues with a different degree. So the exiting photons from the body have different intensity and strength, which in turn they strike the detectors with different strength, with different power. The detectors detect all these photons which exit the body, and via a computer mathematical procedure which is called Fourier transformation, they convert to electrical signals, which in turn they are collected and processed by the computer for the final picture production. Here are some examples of CT scanner images. This table shows the summary of the differences between the MRI and the CT scan, so please take the time to study them with your convenience. If you found this video useful and informative, please put your like and subscribe so you will stay tuned with my channel for any future informative video. Thank you for watching.